So another thing we can find out about functions, not just about increasing and decreasing and where their local max and mins are, but we can also talk about concavity. So we have the concavity test. If f double prime of x is greater than 0, so if the second derivative is positive for all x in an interval I, then the graph of f of x is concave up on I. In other words, think of it as you've got a second derivative is positive, so therefore you're going to be increasing. You're going to be concave up. If the second derivative is negative for all x in an interval I, then the graph of f of x is concave down on that interval. Where we change concavity is known as your inflection point. That's your point where you change concavity. So one of the uses of the second derivative is to tell you where we're concave up and down. There's another use of the second derivative. It also can tell you where your local max and mins are. This is known as the second derivative test because it uses the second derivative. So suppose the second derivative is continuous near some point, C, and if f prime of C equals 0, so in other words, it's a critical point. If f prime of C equals 0 and f double prime of C is greater than 0, then f has a local min at C. Because again, if it's the second derivative is positive, we're concave up, and if we're concave up, you can think of it as that point down there at the bottom is going to be a minimum because you're concave up, you're looking something like this. If f prime of C equals 0 and f double prime of C is less than 0, then we have a local max because you're concave down, that would be a local max up there. And if f prime of C equals 0 and f double prime of C equals 0, then you can't say anything. It's inconclusive. So let's try an example of that. Let's find where g of x, which is equal to 200 plus 8x cubed plus x to the fourth, is increasing, decreasing its concavity, its local mins and maxes, and any inflection points it might have. And then we can actually, from all of that information, graph it. So let's see if we can do this. So first off, my function g of x is equal to, again, it's 200 plus 8x cubed plus x to the fourth. So if we want to find out all this information, we need to have some derivatives. So let's find the first derivative. The first derivative would be 24x squared plus 4x cubed. We then need to set that equal to 0 to find the critical points. So let's go ahead and do that. Let's set that equal to 0. So 24x squared plus 4x cubed equals 0. Factor out of 4x squared, it looks like. And you're going to get 6 plus x equals 0. Okay, so we now have that. So that tells me that we have x equals 0 and x equals negative 6 as our critical points. Now let's also find the second derivative. So the second derivative would be 12x, because we had 24x squared plus 4x cubed. So that means we're going to have 12x plus 12x squared. Sorry, I apologize. 24 times 2 is not 12. 24 times 2 is 48. So we have 48x plus 12x squared. And again, we're going to find out kind of where that is 0 also. So let's set that equal to 0. Factor out, it looks like there's a 12x common. So that will give you 4 plus x equals 0. So even these aren't critical points, they are points of interest to us. X equals 0 and x equals negative 4 is where your second derivative is 0. All right, so we want to know where we're increasing and decreasing. So let's start with that. So if we're looking for increasing, decreasing, we're looking for where the first derivative, and this is why it's very important to write down what each function is, so you know which one you're looking at. We want to know where the first derivative is increasing or decreasing, or has positive or negative, I should say. And so we're going to look at -6, which was one of my critical points, and 0 was the other. If I go back to my first derivative, it was 4x squared with one factor, and 6 plus x was the other factor. So 4x squared was 0 at 0. 4x squared is always positive, so it's positive no matter what side of 0 you're on. 6 plus x was 0 at -6. If you're less than -6, like -7, you're going to be a negative number. If you're bigger than -6, you're going to be a positive number. I have multiplying these together, I have a negative times a positive, which is negative, a positive times a positive, which is positive, and a positive times a positive, which is positive. So I now know that G is increasing from -6 to 0, and then from 0 to infinity. And I didn't include 0 because I don't really know what happens actually at 0. So I usually just go with what areas I have. I know that G is decreasing from -infinity up to -6. Notice I also don't make these closed intervals. I don't know exactly what happens at the endpoints, so I don't want to do that. I want to find out where we're concave up and down. So let's do concavity next. So my concavity looks at the second derivative. So we're looking at G double prime. Again, I'm going to make a little table. So G double prime was 0 at -4 and at 0. Okay, so if we want to find out concavity, we're going to look at where the second derivative is doing. The second derivative was 0 was 0 at -4 and at 0. The second derivative was when we had some factors of that. We had 4x squared. I'm sorry, no, we didn't. I'm going to go back and look. So it had factors of 12x and 4 plus x. So we're going to look at those factors, 12x and 4 plus x. So 12x is 0 at 0. If you take a number less than 0, 12x will be negative. If you take a number bigger than 0, 12x will be positive. 4 plus x was 0 at -4. Take a number less than -4, like -5, you get a negative number. Take any number bigger than that, you'll get a positive number. Then you have negative times a negative, that's positive. Positive times a negative is negative. Positive times a positive is positive. So we want to know concavity. So we want to know what's happening here. So one of the things we notice is that my second derivative is positive from -infinity to -4. And again, from 0 to infinity. So that would be where we're concave up. So G, this is all about G. Even though we're looking at G double prime, it's about G, the function G is concave up on -infinity to -4 and also 0 to infinity. G is concave down wherever the second derivative is negative. And the second derivative is negative between -4 and 0. So we now know some more things about that. We also need to know where our local max and mins are. So even though I used the first derivative test the other time, I'm going to use the second derivative test this time. So the second derivative test says, let's look at the second derivative. Again, that was 48x minus 12x squared. And we're going to look at what is the value of that at my critical points. So my critical points were 0 and -6. So we're looking at G double prime at 0. G double prime at 0, unfortunately, is 0. G double prime at negative 6 would be 48 times negative 6 minus 12 times negative 6 squared. Well, negative 6 squared is positive. Negative 12 times a positive number will also be negative. And 48 times negative 6 is negative. So we've got negative plus a negative. That's a negative number. So the second derivative is negative at negative 6. That means that we're concave down, which tells me that g of negative 6 is a local max. And then you can go back to g and find out what that value is. You can evaluate that and find out what number you get. And you get negative. Did I just say it was a local max? We're not concave down. I'm so sorry. We're concave up. I'm sorry, we're concave down. So if we're concave down, this should be a local min. So I'm trying to figure out what did I do wrong. So let's see here. This is a negative number. This is a negative. That's a positive number. So this is a negative number. So this is negative. And going back to our second derivative test, our second derivative test tells us that if this, yeah, it is a local max. What's going on? So I must be doing something wrong with my calculations. So I do apologize. I realized what my mistake was. I was making a big mistake here. And what my big mistake was is that my second derivative is not 48 minus 48x minus 12x squared. It's 48 plus. So I do apologize. I did not mean to make a mistake. But, you know, we make mistakes sometimes, and we realize when we make those mistakes what's happening. And I realized it was a mistake because it didn't make any sense, my answer. So this is positive, and it turns out that this number, when I go to do it, is actually a positive number because we've got 48 times negative 6 plus 12 times 36. And 12 times 36 is way bigger than 48 times negative 6. So that's a positive number, which means that it is concave up. So it's concave up, which means that we have a local min at that point. And g of negative 6 turns out to be, and again, this is g. We want to find out what g of negative 6 is. We want to find out what that is, and this is why it's important, is negative 232. The problem is I don't know what g prime, g of 0 is because this was inconclusive. So I have a problem here. This is one of the problems I don't like about the second derivative test, but I can use the first derivative test because I already have it. So going back to my first derivative test, I see that I was negative, so I'm decreasing and then increasing. So that means we were a local min, which we now know. And then I was increasing and then still increasing. So that tells me that it's not either a local max or a local min. It's neither. I don't have a local max because we were increasing and then increasing again. So it was inconclusive, but we were able to find out that it didn't have anything going on. So we don't have any local max. The other thing we need to also know are where we have inflection points. Inflection points are wherever we change concavity. So we change concavity at -4 because we went from positive to negative. And then we change concavity at 0 because we went from negative to positive. So we in fact have inflection points. And the inflection points are g of 0. And g of 0 is, if you go back to your function, g of 0 is going to be 200. And we also have an inflection point at negative 4. And g of negative 4 is negative 56. So our reminder is this is why it's really important to label your functions and your derivatives, because knowing that then what g of negative 4 tells me I'm going to go all the way back to my g function and plug into that function there. I don't ever really plug into my derivatives for those because I'm using those derivatives to just find out if they're local max or mins, and when we're increasing, decreasing. I'm using the second derivative to find out where we're concave up and down, but I want to know what g is doing. So now I have all this information about g, I can now graph it. So let's go ahead and do a graph of this. So we need an axis. We are having negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. Let's do negative 7. We'll do 1, 2, 3 on this side. What I also noticed is that my numbers were like negative 232 and negative 56 and positive 200. So that might mean I might want to count by 50s, let's say. So we'll count by 50s, 50, 100, 150, 200, 250, minus 50, minus 100, minus 150, minus 200, minus 250, and we'll go all the way down to minus 300, let's say. All right, so now we can go ahead and plot those points we know. We happen to know some points. We happen to know that our local min is at negative 6, negative 232. We happen to know that our inflection points are 0, 200, and negative 4, negative 56. So we can plot all those points. So negative 6, negative 232 would be right about here. Negative 4, negative 56 would be right about here. And 0 to 100 is exactly right. Well, not exactly because our graph's not perfect here. And then we can go ahead and graph it. We know we were decreasing. So let's go back and look to see where did we say we were decreasing. We're decreasing from negative 6, from negative infinity to negative 6. We're increasing from everywhere else. Okay, so we can now look at this and say we're decreasing from negative infinity to negative 6. That's where we had our minimum. Then we were increasing. We're still, by the way, let's look at our concavity. We were concave up from negative infinity to negative 4. So we know we're going to be concave up, and then we're going to be concave down from negative 4 to 0. So we know we have an inflection point at negative 4. So we know we're going to change our concavity here. So we're now concave down. And then at 0, we change our concavity again, and we're concave up again. So there's our graph of G. I didn't need a calculator. I didn't need anything else. I got all of that from just my derivatives and my first and second derivatives. We'll do one more. Let's find out where this function x q of x equals x minus 3x to the 1/3 is increasing, decreasing, concavity is local min and max, and its inflection point. So again, we're going to start off by knowing the derivatives. So let's take the derivative. So the derivative of this would be 1 minus x to the negative 2/3. We're going to go ahead and set that equal to 0. Let's go ahead, just for the fun of it, let's find the second derivative. So let's find our second derivative. Our second derivative would be 2/3. Can't read my own handwriting. 2/3 x to the negative 2/3 minus 1 would be negative 5/3. Okay, and the derivative of 1, of course, was 0. All right, so now let's find out where are both of these 0. So we're going to set both of these equal to 0. We also want to know where are they both undefined. So we didn't look at the other one for being undefined because we had a polynomial. Polynomials are never undefined, but this one's not a polynomial. So that's what tells me, look at the undefined part. It might also help me to take my derivative, which was 1 minus x to the negative 2/3, and write that as 1 minus 1 over x to the 2/3 equals 0. Well, that won't ever equal 0, right? Because if you were to go ahead and combine that together as a function, I mean, as one single fraction, I should say, you can have x to the 2/3 minus 1 over x to the 2/3 equals 0. Well, that would mean that x to the 2/3 minus 1 equals 0. So it will actually equal 0. So that means x to the 2/3 equals 1. So that's going to equal 1 when x equals 1. So if that's one value, let's also look to see what's undefined. It's going to be undefined when your denominator is 0. So when x to the 2/3 equals 0. So that's when x equals 0. So there's our two critical points, 1 and 0. So let's put them on a number line. Here's 0, here's 1. We're looking at our derivative. So we're looking at q prime. I like to mark that so I remember which one this belongs with. Then I happen to have x to the 2/3 minus 1. That's one factor, and x to the 2/3 was my other factor. So x to the 2/3 minus 1 was 0 at 1. If you take a number less than 1, like 0, you're going to get a negative number. If you take a number bigger than 1, like, I don't know, 8, you're going to get a positive number. X to the 2/3 really isn't 0 at 0, but it was undefined there. So if you take a number less than that, you're still squaring it. So no matter what, it's going to be positive. Because x to the 2/3 means you're going to take the cube root and then you're going to square it. So you're always going to get a positive number. So positive times a negative is a negative. Positive times a negative is a negative. Positive times a positive is a positive. So now we know that Q is increasing from 0 to 1, and then again from 1 to infinity. And granted, well, what did I just do? I don't mean to make mistakes. It's getting late. That's probably why. It's only increasing from 1 to infinity because we changed signs. So remember, it's where the derivative is positive. So it happens to be from 1 to infinity. Q is decreasing. This is the one that's got the change here. Whenever the derivative is negative. So that's going to be from negative infinity to 0. And also from 0 to 1. I don't include the 0 because I don't know exactly what's happening at 0. So I try to not include that one. Okay. So now let's go ahead and find where what we can do. Let's do the increasing local max and mins. So we're decreasing and then we're decreasing again. So at 0 is neither a local max nor a local min because we don't change anything there. We are then decreasing to 1 and then we're increasing beyond that. So we're going down and then we're coming back up. That will be a local min. So there's a local min at x equals 1. The local min is actually q of 1. And again, it's q of 1. So you're going to go back to your original function. My original function was q. Q was x minus 3x to the 1/3. So my original function is x1 minus 3 times 1 to the 1/3. So we have a local min, and it's going to be -2. I do want to point out your local mins don't always have to be negative. It just happens to be in these two examples they were, but they don't have to be. Now let's go find concavity. So that means we're looking at the second derivative. So let's take our second derivative, which was 2/3 x to the -5/3. We want to know where the second derivative, which was 2/3 x to the negative 5/3. We want to know where that is 0 and also where it's undefined. So first off, I would rewrite this as 2/3x to the 5/3. Well, that actually will never equal 0 because you got a 2 on the top. 2 can never equal 0, so this is never. So it never is 0, but it is undefined. It's undefined wherever your denominator, 3x to the 5/3, equals 0. So at x equals 0, your function, your derivative, your second derivative is undefined. So let's look at the second derivative and what's happening there. Our factors again are 2/3 x to the negative 5/3. Well, if you take a number that's going to be undefined at 0, if you take a number less than 0 and you raise it to the negative 5/3, it's not going to change the sign, so it's still going to be negative. If you take a number bigger than 0, it's going to be positive. So our second derivative is negative less than 0 and positive greater than 0. So I can now get my concave cavity. We are concave up wherever the second derivative is positive. So from 0 to infinity. And we are concave down from negative infinity to 0. We could think of having an inflection point there because we are changing concavity. So you could say we have an inflection point q of 0. Again, that is q. So you're going to go back to your original function. My original function was x minus 3x to the 1/3. So my inflection point would be 0 minus 3, 0 to the 1/3. So my inflection point is the point 0, 0. So I now know where we're concave up and down. I know where we have local max and mins. We actually have no local max. We have a local min. I know where we're increasing, decreasing, and I know where I have an inflection point. And from all that information, I could actually go and graph this if I wanted to. I will leave that for you.